Okay, this video is about Gram Schmidt orthogonalization. Okay, so the thing we want to solve with Gram Schmidt orthogonalization is suppose that we're given a set of vectors, this set of vectors T, okay? It's a finite set, 1 through n, and these vectors may or may not be orthogonal, and they may not be orthonormal, so they don't form an orthonormal set. So, for example, set of polynomials, 1 t squared over 2, t cubed over 3 factorial, etc., up to some finite value, would not be orthonormal to each other. So the question is, how do you orthonormalize? How do you produce from here another set, T prime, that spans the same space? So we haven't added dimensions to the space or anything. It spans exactly the same space, but all of the vectors are now equal to, so this delta ij is the Kronecker delta product. It's 1 when I is equal to j, and is 0. So in other words, this is 1 when I equals j, and 0 when I is not equal to j. Okay, so in other words, how do we orthonormalize this set? And there's a nice algorithm for doing this that works for any finite set of vectors. It's called Gram Schmidt orthogonalization. Okay, so I'm going to describe the process that you go through to orthonormalize this set. Okay, so the first thing you do, step 1, is to normalize the first vector. So we're going to just pick out P1. We'll pick P1 out of this set, and we're just going to divide it by its norm. And so we know now that Q1 is at least unit length, right? So this says that the norm of Q1 is equal to 1. All right. Now, the next step is what we're going to do is we're going to take Q2. So here we want to construct Q2. So here's P1 and here's P2. Okay, so P1 and P2, we assume that this original set, by the way, T is going to be linearly, we assume that this is linearly independent. Okay, and in fact, Gram Schmidt orthonormalization will tell you if they're not. All right, so we have P1, we've normalized it to get Q1, and now let's look at P2. And what do we do to get something that is orthogonal, a Q2 that is orthogonal to Q1 and also normal? Okay, so we're going to let the air, we're going to look at, yeah, I guess I have a typo here. That should actually be Q2, and this should be, that's equal to, what we could do is call this Q2 prime. Yeah, this would be Q2 prime. Okay, so what this vector is here, what this guy is we're going to take P2, okay, this is P2, and we're going to subtract from it the, so if we take P2 inner product with Q1, that's going to be this guy right here, right? That's P2 inner product with Q1. In the direction of Q1, that would be this vector. And so we're going to take, so this is the vector that lies along Q1. It's basically how much of P2 lies along Q1. And we're going to subtract that from P2. So we're going to have, this vector minus that vector means we come straight back like that. And it's going to give us something that lines up exactly with Q2. Now, that, in other words, it lines up with, it's going to give something that is in fact orthogonal to Q1. And one way you can see that is if you take P2 minus the inner product of P2 Q1 with Q1, and I inner product that with Q2. Okay, what happens? This is going to be the inner product of P2, with P2. I want to show that it's orthogonal to Q1. So let me rewrite that. I apologize. So this is going to be P2 minus inner product of P2 with Q1 times Q1, and I want to inner product that with Q1. In other words, I want to show that this vector here is in fact orthogonal to Q1. So this is going to be P inner product of P2 with Q1 minus the inner product of P2 with Q1 times Q1 inner product with Q1. And now this is a scalar that we can pull out, so that'll be P2 minus Q1, or inner product with Q1, minus, and now we'll have this guy pulls out, P2, inner product of P2 with Q1, and what's left is the inner product of Q1 with itself. And we know that, in other words, this is equal to P2 inner product with Q1 minus P2 inner product with Q1. And this guy is just the norm of Q1 squared. And the norm of Q1 squared is equal to 1. So this is all equal to 0. So in fact, this vector here is orthogonal to Q1. Yeah, now I see what I was doing here. We can let that be equal to E2. Okay, so this is E2. I like that notation. And then Q2 is just going to be, or it may not be unit length, and so we'll normalize. And now we have Q2. And then we keep on going. So when we get to the kth element, we're going to let EK be PK, and now what we have to do is we have to subtract out how much of PK is in the direction of each of these, is in the direction of Q1 times Q1, minus how much is in the direction of Q2 times Q2, all the way up until QK minus 1. And so this will be, PK, and then we've subtracted out how much of PK is already described by the other elements, Q1 up to QK minus 1. So that's going to be EK, and then QK is going to be we just take the unit length. We do that up until they're in vectors. So that is the process of Gram Schmidt orthogonalization. And maybe let me, let's see, so if I insert a page, we can construct an example really quick. So suppose I have the vectors, so my original vectors T is going to be, the span of these three vectors. Maybe let's say 1. Let's say 2, 1, 2, 0, 0, and then maybe we'll do 1, 2, 0. This is going to be relatively easy, and then we'll do, 1, 2, 3, like that. Okay, these guys are linearly independent, but they're not orthonormal. So how would we go about? So this would be, in other words, this is P1, this is P2, and P3. So Gram Schmidt orthogonalization or orthonormalization would say, okay, we'll first set Q1 equal to P1 divided by the norm of P1, which is going to be 2, 0, 0 divided by the norm of 2, 0, 0, which is 2. So 2, 0, 0 divided by 2, we'll have 1, 0, 0. Okay, that's Q1. Now, we're going to let E2 be P2 minus the inner product of, we want to have P2 with Q1 in the direction of Q1. So that's going to be 1, 2, 0 minus the inner product, and for vectors, the inner product is just the transpose, so it would be 1, 2, 0 transpose with Q1, which is 1, 0, 0. Okay, that's going to be the inner product times Q1, which is 1, 0, 0. And that is going to be equal to 1, 2, 0 minus, now when I take the, so the dot product here will be 1, minus 1, 0, 0. And so that's going to be 0, 2, 0. And Q2 is going to be E2 divided by the norm of E2, which is equal to 0, 2, 0 divided by 2. So we'll get 0, 1, 0. All right, so that's, we've now found Q2. And now E3 is going to be P3 minus the inner product of P3 with Q1 in the direction of Q1 minus the inner product of P3 with Q2 in the direction of Q2. So this is going to be P3 is 1, 2, 3 minus, and then we have the inner product of 1, 2, 3 with Q1, 1, 0, 0, all in the direction of Q1 minus now the inner product of 1, 2, 3, 1, 2, 3 with Q2, which is 0, 1, 0, and in the direction of Q2, like that. And so we've got 1, 2, 3 minus, and then when we take the inner product, we'll have 1 plus 0 plus 0, so minus 1, 0, 0, and then minus, now the inner product here will be 1, 2, so we'll have 2 times 0, 1, 0, and so this obviously gives us 0, 0, 3. And so Q3 is going to be E3 divided by the norm of E3, which is 0, 0, 3 divided by 3, 0, 0, 1. Okay, so an orthonormal set that spans the same space, all of R3, would be, the span of 1, 0, 0, 0, 1, 0, 0, 0, 1, as we would expect. This isn't the only set, but it's the set we get from Gram Schmidt orthonormalization starting with this particular t. And this is going to be equal to the t prime. So there is a very simple example of